Yeah, good afternoon, Chairman and everybody. In the next few minutes, we're just going to look at the impact of including polygenic effect in genomic evaluation using the Bayesian methods. Most countries, currently we fit a G-block model. We use SNP from the 54K chip, and we sort of assume that it explains all the genetic variation. However, we are aware that in a number of countries we include a polygenic effect, just to account for the fact that we may not explain all the SNP will not explain all the genetic variation. The work from Liu have already shown that the optimal level of the residual polygenic effect may be different for different traits. Also, it might help traits of lower heritability to pass the interval validation test. However, it is unclear what really happens when we fit a polygenic effect, and I thought I hit a black box. I just wanted to lift a little bit. So I wanted to see what is the impact, for instance, when we have a polygenic effect, what effect does it have on the SNP variances and effects in terms of SNP with different alleles or different frequency. I wanted to look at what happens to the composition of the polygenic solutions in terms of both with different amount of information. And instead of fixing the polygenic effect, why don't we try to estimate it and see what impact it will have on our evaluations? So basically, that is the aim of the study. We look at different levels of polygenic effect, our genomic evaluation for make yield as a trait of high to medium heritability, and somatic cell count as a trait of low heritability. I've used G-block base A and base B. We look at the accuracy of genetic predictions. We look at the effect of the SNP effects and variances. We're looking at SNPs of different frequencies. And then look at the composition of the polygenic solutions in terms of contributions from parent average, de-regress proofs for both with different amount of information. The data consisted of just over 11,000 host and freezing both with 50K genotype. We carry out the usual SNP edits, and we ended up with just over 41,000 SNPs for the analysis. A linear model was used for the analysis in terms of having a mean effect, a random residual polygenic effect, and a random SNP effect, and an error in term in the model. We look at different levels of polygenic effect, 0, 5, 10, 15, 25, of the total genetic variance. I will try to unconstrain the polygenic effect using base A and base B. 18,000 cycles of Bayesian methods were carried out, and the first 24,000 were regarded as born-in period. And 20 MH cycles were carried out within the Gibbs sampling cycle for base A, for base B, and 70% of the SNP were assumed to be non-zero variance. The regress proofs from the April 2011 were used for this run, and also Maze proofs were used as well as independent variables with ADCs as weighting factors. Okay, just to give you an idea what the reference population was like and the validation set, we had a minimum of 10 EDCs and a reliability of 69 to be included both in the reference and in the validation set. Basically, we used 2004 as the cutoff point, year of birth. We have just over 8,000 bulls in the reference for Merck, 4,000 roughly for validation set. For somatic second, just around 7,000 and just over 2,000 for somatic second. We look at the accuracy of validations in terms of the relationship between the DGVs and the regress proofs in the validation set. Now we'll move on to results. So basically, here we have the regressions and correlation between the DGVs and the regress proofs in the validation set. The first conclusion or what is clear is that the regressions and correlations were higher with G-block than base A and B, and base B comes second. The second thing, if you look at it, you find that the stepwise increase in the regressions are more at the initial stages until you get around 10% of polygenic effect. For milk, and basically the stepwise increase is very minimal, so you can sort of decide what's an optimum level there. I think that's just what I wanted to say about this slide. We'll move on to the second one for somatic second. Again, we have similar picture, but the results, again, I didn't complete base B before the conference, but the results are very similar in terms of when you have a polygenic effect in the model for G-blob and base A in terms of the regressions and correlations. Apart from when, for instance, you have no polygenic effect, then the regression and correlation are very poor for base A. Again, the stepwise increase in the regressions were much more at the beginning of the level of polygenic effect until you get around 20%, and then actually there was very little stepwise increase in the regression. So you might decide from there what's the optimum. This slide shows the correlation between the SNPs and the polygenic component with the DGV at each level of residual effect. As you would expect, the correlation decreases for the SNP effect as you increase the level of the polygenic effect, whereas the correlation for the polygenic effect increases. But what I wanted to find out at every level of polygenic effect, I found that the correlations were always higher for somatic cell count than for milk production, which gives us an indication that parent information, for trace of low heritability, polygenic effect may have more influence. And now when we look down, sort of look at the composition of what really happens to the polygenic solutions, I've looked at it at both with different amount of information. For instance, we look at milk yield when you have EDCs of less than or equal to 15, you can see that at 5%, 81% of in the polygenic solutions actually coming from parent average. And that is quite substantial. Even as you go up to 50%, you still have 59% coming from the parent information. But however, when you have just 100 or more ADCs, then the parent average have little or no contribution at all. But when you go to somatic cell count, even with an ADC of 100, at 5% polygenic, 95% of the polygenic is essentially parent average. And that holds quite substantial, even up to 25%. You still have 75% of that composition, of that polygenic effect coming from parent average contribution. This next slide shows what is the impact, for instance, of including the polygenic effect on SNPs of different frequencies. And it's quite consistent across the various methods. So when you have polygenic effect for SNPs with low frequency, there is an increase as you actually increase the level of polygenic effect. That is whether you say 21% for G-blob, 69%, 46% increase as you increase the level of polygenic effect. And quite consistently, for medium to high frequency SNPs, we found that you're actually decreasing the SNP effects. But however, life is not always straightforward. The same picture is not repeated for somatic cell count. It's rather there's no ray pattern, but you can see that again, the low frequency decreases for G-blob, whereas it's a bit more stable for base A, and there's a sort of variation whether it goes up or down. It's not very consistent compared to what we saw with milk yield. And then when we look at the impact of having a polygenic effect in the model on the variances different from base A and from base B, you can find that as what you would expect, as you increase the level of polygenic effect, there is a decrease in our SNP variances. But when you look, for instance, at SNPs of high frequency, the decrease in the variance is quite dramatic. It's much more compared to low and medium frequencies. And that's also the same picture sort of applied even for base B slightly, not as dramatic as base A. What happens, however, when you do not put any constraint on the polygenic effect, the result wasn't what I was expecting at all. I found that the percentage of the variance accounted for by the polygenic was 65%, 49% for milk and somatic cell count in base A, very high. And the similar estimates you get when you use base B. It could well be that when we have a whole relationship matrix in with our polygenic effect, the model is find it quite difficult to partition the first appropriately. I put a question mark there, just in case someone had a better explanation. So consequently, because the proportion of polygenic is very high, this model, they have a low predictive ability, especially for mercury. Coming to conclusion, we find that the predictive ability of G-plot was generally higher than the Bayesian method for both traits considered in this study at different levels of polygenic effect in the model. The contribution of parent average to your polygenic solution could be substantial at low levels of polygenic effect in the model, especially for boosts with few traits. And the consequence is that as these boosts accumulate more daughters, there will be a change in their proof, not because of what is going on in terms of the SNP solution, but rather what is going on with your polygenic component of your DGV. I feel that the choice of optimal level may involve a careful consideration of several factors, maybe the regression coefficients, correlations, mean-square errors in the validation set, and maybe you need to consider the possible influence of PA at the level of residual polygenic effect. Increasing the levels resulted in increasing trend in SNP solutions for mercury for SNP with low frequency, whereas the opposite was the case when you look at medium to high SNPs, SNP with medium to high frequencies. No clear pattern for somatic second. The SNP variances decline with decreasing levels of polygenic effect in the model was much more dramatic when for SNP with high frequency. The variance estimate for polygenic effect, which were considered were too high and a bit difficult to explain. Just to acknowledge the funding by Derico and access to genotypes for CDDR and ANAFI, which used for this study. People contributed programs to Clubware. I modified these programs for this study. And also part of the high-density genotypes came from the UK Ruminal Genetic Improvement Network, which was funded by DEFRA. Thank you very much.